people are talking about some astronomer terms for coordinates and.
Oh yeah.
I think there's about 5 different classes of coordinate systems in astronomy.
That seems well. I guess it isn't unnecessary. Is there is there a reason, or is it just because people didn't talk to each other?
So they are useful in different contexts. So one coordinate system is an observer's coordinate system. So you like straight overhead is one pole of the coordinate system, and like the equator is the horizon.
Right, but if you are measuring one object relative to another object, then using that coordinate system doesn't make a lot of sense.
No, but like if you're talking about where to point, like what commands you should tell the telescope to point. There's another coordinate system where we take the equatorial coordinate system where we project the north and south poles as the coordinate, and the equator is the equator projected.
Right.
That's probably the most common. There's another coordinate system where the path of the sun across the sky, the ecliptic, is the equator, and that's very good for talking about things in the solar system.
Oh, okay. Because
most of the planets and such are all in the same plane. There is another coordinate system where you use it's very useful for talking about stuff in our own galaxy, where the plane of the galaxy, our galaxy, is the equator, and somewhat,
which is, and like the plane of the galaxy is almost the ecliptic, isn't it?
It's actually quite
close?
It's quite tilted.
Oh, really?
If you've been lucky enough to be at a place dark enough to see the Milky Way, you see the Milky Way is at quite an angle to the. So that's a very useful coordinate system if you're talking about stuff in the galaxy, because there's a lot of stuff in the disk, and
right.
So like one coordinate is like how far along the disk it is, and then the other coordinate is how far above and below the disk it is. And then there's another coordinate system that isn't used very often, so it turns out a lot of the galaxy, you can draw if you take the galaxies that are near our own galaxy, and near in this case, we're talking tens of millions of light years.
Right.
Because space is big. And if you draw a plane through that, or it turns out you can draw a plane through a lot of the local galaxies. And the way galaxies are distributed in space they're sort of in planes and filaments, and there's voids between them. But you can set up a coordinate system such that all the galaxies are in a plane, but that's not used very often.
So the idea, like, all these coordinate systems have the same actual, like, scale. They're just where your 0 point is.
Yeah.
And it just makes it so that the calculations don't have huge numbers on all the different things. Basically.
Yeah. So depending on what problem you're working on, so that's a lesson in physics. Is you can change you change the coordinate system. It doesn't change the physics.
Right.
So you pick the coordinate system that is most convenient for the task at hand. And while spherical trigonometry is horrible, people have taught computers how to do it. So the computer can do it all for you. There was one class where the prof tried to teach us spherical trig, and I haven't used it since. It's all been use a software library someone else has written.
But you have to know it well enough to know what to ask the computer.
Yes. Yeah.
Trick. Yeah.
Yeah.
I saw that there's on Amazon Prime. There's the really neat documentary about the Voyager probes. They're going out, and it's like the quiet of space or something. It's talking about just the small team that has been charged with that has been charged with keeping those Voyager probes going far beyond their original mandate. all the ridiculous things they have to do, not only to keep them going, but just to like find them. Like they keep losing, like sometimes they lose track of them, or the satellite, the big array in Australia, they had used it because of how the orientation of the planet. I guess they had to use this big, they had to use a big radio telescope in Australia to do to contact it, which that telescope had to go offline for like 6 months or something, and so they were like, there's a reasonably good chance we won't be able to find it again.
Yeah, so the there's actually I don't actually know, one of the big radio telescopes in Australia that is sometimes used as part of the Deep Space Network is the radio telescope at Parkes, which is famous for being part of beaming back the moon landings.
Oh, cool.
So of course, like, it's the largest dish in the southern hemisphere. So if you're trying to beam back a television signal, you're going to try and use the biggest one. And there's a really good movie called The Dish that's about getting the TV signal from the moon landings back through the Parkes telescope.
Cool.
And it's this sort of funny thing that there's all these Australians out in the bush, and this guy from NASA shows up, and it's a comedy. But at one point, like
it's a fictionalization.
There's creative liberties have been taken.
Yeah.
And there's a good bit in it when they're trying to do all the. This is the late '60s, and math is hard. Computers are not.
They haven't got the told the computers how to.
So they're
trigonometry yet.
There's a case where maybe NASA has a computer that could do that calculation for you, but in the bush in Australia, I'm making Parkes sound like more of a. Admittedly, the telescope isn't a sheep paddock.
Well, they have to sort of have it away from other electromagnetic interference, right? I have a story about that as well. Not my own story. One of my friends in grad school. But at one point, they like lose track of where the Apollo 11 is, and they're trying to do all the really crazy math and figure it out. And then one of the guys' reasons like, just point the telescope at the moon. It's somewhere around there.
Yeah, it's close enough. So the dish is used. Parkes is used for a lot of science today, and one of the things is fast radio bursts. These unexplained bursts of really strong, bright radio frequency, and
that we don't know what it's from.
We have a. Let's go with that. That's that. We have a better idea now, but when they were first, so they first discovered one, and they didn't see anything, and then they saw these things that were like fast radio bursts, but they were fairly certain were radio interference.
Right.
And so that cast doubt in the on the existence of this first one. And then many years later, they started finding more as radio receiver technology improved. They started finding and data processing improved. One of my classmates in grad school, their PhD was on how to program GPUs to do a particular type of data processing for. And this is like 15 years ago when programming GPUs is fairly new. So people eventually accepted that these fast radio bursts were real. And then another friend from grad school, one of the things she did was she figured out that these fake, these signals were coming from the microwave in the break room. I think in the wool shed or like a name like that. And because they looked at when did these signals come from, and they peaked around noon during workdays.
So there were also real ones.
Yeah.
But there was all this interference from the microwave.
So somebody was opening the microwave before it was finished, and some issue with this particular model of microwave spat out a bunch of stray radio frequency energy that was enough to show up as a fake signal on the.
It's like because it's like that. It's like why would something in this sort of celestial world pay attention to what time is lunchtime?
Yeah.
Right. So you're sort of like
suspicious.
Wait a minute here.
And I think my understanding of the most recent science is that it's magnetars that are producing the fast radio burst. So a particular type of neutron star.
Okay,
Something about something magnetic fields. But then again, if astronomers don't understand something, they invoke magnetic fields. Because it turns out magnetic fields are complicated.
It's amazing. Like I always think about astronomy. It seems like in a lot of ways, you know, astronomy and like I don't know, something like sort of like archaeology have a lot of like, you know, an archaeologist will look at like, you know, they'll have like the you know, the toe bone of a Tyrannosaurus Rex and be able to like reconstruct what that Tyrannosaurus Rex looked like.
Well, that would be a paleontologist.
I guess. Oh yeah, I guess that's true. Or I guess that's paleontologist, archaeologist, but same deal with archaeologists, like being able to infer huge amounts of information based on a very small thing. And by the same token, you know, the astronomers who can, you know, the thing where you sort of go, that star has a very slight wobble to it, and we can then figure out what and you know we can figure out that there might be not only that there could be a planet around it, but approximately where, you know, what orbit that planet might have, and then if we can catch the planet crossing the sun, we can actually get a spectrum of what the planet is, and we can start being like, and it's like really, it's like we're basing this all on just a teeny weeny wobble on that thing, but it's amazing what can be.
It's amazing how some of the information you can get out. And I can remember, like, one of the projects I worked on, I was measuring how fast clouds of gas that are billions of light years away were moving towards us or away from us. Because it turns out that's an easier measurement to make. No idea how it's moving this way, how it's moving this way. Dr. Becky is a good astronomer outreach person.